All right, so our goal is to move into studying a little bit of a new object called a vector space. And before we start that formal abstract definition of a vector space, we're going to think about one that we're all pretty familiar with. So R2 is a vector space over R. And that over R language I'll come back to in a minute to explain a little bit more. But R2, this is just like the XY plane that we're used to, except instead of thinking about points on the plane, so instead of thinking about maybe a point x comma y, we think about vectors on the plane. Okay, and so that vector I'm going to write with these sort of angle brackets like this to remind ourselves that we're talking about a vector, not a point. And so vectors are these objects with length and direction that point in a particular direction toward a point x comma y from the origin. All right, and vectors have some properties that are going to seem familiar to you. So we can add vectors. So if I took a vector 1 comma 2 and I wanted to add the vector 3 comma 4, I do that by just adding the components. I add the x coordinates together, so 3 plus 1 gives me 4, and I add the y's, 4 plus 2 gives me 6. Okay, and in this addition, I have lots of those properties we were looking at when we were studying groups and rings and fields. So this addition is commutative. The addition is associative. I have additive inverses. I have additive identity called the zero vector. The zero vector is just 0, 0. And that's an additive identity. If I add it to any other vector, so maybe AB plus 0, 0, I get AB. So it's the additive identity. And then I have some kind of multiplication on vectors, but it's not quite similar to what we were doing with rings and fields. We can multiply vectors not by each other, but by scalars, okay, by constants. And that by scalars, that's where this over R language comes in. So that over R is talking about what scalars we can use in this multiplication. Okay, so when we multiply vectors by scalars, that means if I have a real number, I'll call it C, and I want to do C times the vector xy, I just bring that c inside. It becomes cx times cy. Okay, and so this multiplication is not similar to how we had multiplication in rings and fields because you're multiplying different things. You're multiplying a scalar, a number, by a vector, which is different. But lots of the familiar properties are still true, addition and the scalar multiplication. So they're both associative. We have a distributive property of a scalar multiplication multiplying times a sum of vectors. Lots of stuff is going to carry over from that last chapter. All right, and so we can also do this with other vector spaces. So vector spaces like R3, and again over R, or R4 over R, or really any Rn over R. Okay, and so what I mean by that is I can make my vector as long as I want. I can have a vector that's an x1, x2, dot, 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 all the way up to xn, and I can add it to another vector that's maybe y1, y2, up to yn. So I can use these same kind of properties in whatever dimension I want. All right, so one more thing that we're going to be using in terms of vector spaces is that we can decompose vectors in a useful way. Okay, so I'm going to do some examples of this, and then you'll do some examples of this for some homework in a little bit. So, for example, if I take a vector A comma B, and I want to write it as some combination of two other vectors. So these are standard ones, 1, 0, and 0, 1. These two vectors often are given a name, I or j is what they're sometimes called. And so I put these blanks here, so we're going to try to fill in those blanks. So if I vector AB as this combination of I and j of this 1, 0, and 0, 1, that's not too hard to do. I just do it's A times 1, 0 plus it's B times 0, 1. And I can do that with any vector I want. So 1, 7, I can write as 1 times 1, 0 plus 7 times 0, 1. Okay. And there's nothing, so I and j are special because they're easy, but there's nothing special about those two vectors. There's nothing specific about being able to use only those two vectors. So like I could take 1, 7, and I could try to write it as this combination of the vectors 1, 2, maybe, and let's try 2, 4. How about? Nope, 2, 4 is not good. 2, 3. All right, so again, I'm going to try to fill in those blanks. Okay, so my goal is to figure out what goes here and what goes here. So I'm going to call them x and y for right now. And let's do out this problem. So I'm going to just kind of simplify this example by distributing that x in. So x, 2x. And then I've got a 2y and a 3y. Okay, and then I can add those. So now I have 1, 7 is supposed to be x plus 2y and 2x plus 3y. And now what this means is that 1 has to equal x plus 2y, and that 7 has to equal 2x plus 3y. And now I have a system of equations that I can solve. So I want to solve this anyway. I know how. Find x and find y. All right, so what do I want to do here? So I might want to take that top one and multiply it by 2, because if I do that, and I put it down below, I'll get a 2 is 2x plus 4y, and then I can subtract these. So if I do that, 7 minus 2 gives me 5, 2x minus 2 gives me 0, 3y minus 4y gives me minus y, and so now I know what y is. Y is negative 5. And if I know y, then I can find x by using one of those equations up above. So I might go back to that top line for a second and say, if y is minus 5, then that top equation was 1 equals x plus 2 times negative 5. And so x is going to be 11, it looks like. All right, so what I just did was write that 1, 7 is, let's see, 11 times 1, 2 plus negative 5 times 2, 3. And we should be able to check that this works by just kind of multiplying stuff out and adding. All right, so there's lots of ways I can do this. There are lots of vectors I can choose and try to solve this kind of system. There are some vectors that I can't choose, and there's a question about like, did I only use 2? Maybe I could use 3, maybe I could use 1. What can I really do and what can I not do here? I want to do one more thing with you, though, before I have you do some of these little calculations, and that is, so I did this with a very specific vector, 1, 7, but can I do this with any a, b with those same two vectors that I'm trying to decompose into? So what I mean is if I had a, b, and I wanted to, again, fill in these blanks with the vectors 1, 2, and the vectors 2, 3. So I'm trying to express AB in terms of those two specific vectors. This is going to be really similar to the problem we did up here, but more general because now I have AB instead of 1, 7. But I'm going to proceed the same way. So I have an X and a Y that I'm trying to find. My goal is to solve for X and Y. And I'm treating A and B as kind of given numbers. So now I have A, B, and I'm going to do all that combining at once. So if I bring the scalars in and add together, then I get an x plus 2y and a 2x plus 3y. That should look familiar. And then we have two equations. We have a system of equations. So I have A is x plus 2y, and I have B is 2x plus 3y. This should look similar to the. And again, I'm trying to solve this. But here it's a little more unclear. We've got 4 variables, so we need to keep in mind what we're trying to solve for. We're trying to solve for x and y, not a and b. We're treating a and b as like givens. All right, so I want to isolate x, I want to isolate y. I might do this differently than I did above. So I might do something like, just so you see another technique, maybe let's solve that for x. So I have x is a minus 2y if I subtract 2y from both sides. Okay, so now I know x in terms of a and y. Maybe I'll do the same thing with b. So let's go down here and say, if I solve that equation for x, I get that 2x is b minus 3y. And so x is a half b minus 3/2 y. All right, and now this is a system of equations, so they both want to be true at the same time. These are both solved for x, and so putting those two together is a minus 2y is a half b, I'm squeezing myself in too close here, minus 3/2 y. So now let's go with that and see what else this tells us. So remember, I'm trying to solve for x and for y. So I'm going to combine some like terms. I've got y's on both sides. Let's add 3/2 y to both sides. So I'm going to have a minus 4/2 y. Let's get a common denominator. Plus a 3/2 y is a half b. Okay, so a minus a half y is a half b. So minus a half y is minus a plus a half b. You may have found a much better way to do this algebra, and that's awesome. I think you should do whatever way makes sense to you. I'm just kind of trying to do one so you see it. All right, so we solve for y and we get y multiplying by negative 2. So I get a 2a minus b. Looks good. All right, so there's my y. I've done a good bit of my goal, which is to solve for x and y. And when I say that solve for x and y, it should make sense that this is in terms of a and b. We're not going to be able to get rid of a and b. We just need to know what's x in terms of a and b and what's y in terms of a and b. And we have that for y. Now we can use this to get x. So if you look at the top of the screen, we know that x is a minus 2 times y. Okay, and so we can simplify and we get that x is a minus 4a, so minus 3a, and a plus 2b. It looks like, sorry, no. We have our a minus 4a plus 2b. All right, so there's our x and our y. So if we sum up what we just did, what we did was write any vector a, b as this scalar, minus 3a plus 2b. Whatever a and b are, you find that number, times the vector 1, 2, plus whatever a and b are, you find the number 2a minus b, times the vector 2, 3. And so that's how we can break this vector AB up into a combination of these two vectors, 1, 2, and 2, 3, which I gave us to start with. All right, so now you're going to play around with a little bit of this. This idea of decomposing vector is what's going to be useful to us. So I'm going to give you some examples to try and to think about why they work or why they don't work.